Hello math fans. Here's a problem we're going to work on today. We're going to try to determine how large n must be so that the partial sum, s sub n, estimates this series, the sum n goes from 0 to infinity of minus 1 to the n over n factorial. I want that partial sum to be accurate to within 3 decimal places. Okay, so what we're going to use is the alternating series estimation theorem. Now first, we should note that it's clear that this series converges by the alternating series test. If you just pick off the portion of the terms which doesn't include the minus 1 to the n, then that portion is a sub n equals 1 over n factorial. So you can see that down here. Okay, that part is decreasing and it definitely goes to 0. That much is easy to see. Okay, so now we're going to use the alternating series estimation theorem. Now that says that the absolute value of the remainder is always smaller than the next term in the series. So if you estimate that sum by taking a partial sum, you can bound the remainder by the next term in the series. All right, so I want to make a sub n plus 1 smaller than 0.0005. Okay, so keep in mind we're looking for 3 decimal place accuracy. And so the reason I've chosen this number is because the way that we do rounding is you look at the next term, and if that's greater or less than 5 in that digit, then you're going to round off. So 3 decimal place accuracy, in order to get that, then you need to go down to 0.005 to get a 3 decimal place accuracy. Okay, so if we can make a sub n plus 1 smaller than 0.0005, that's going to be what we need to guarantee 3 decimal place accuracy. Okay, so what we'll do is we'll just look at a few terms of the series. Okay, so let's take this series and just write out a few terms. All right, so first if I just write them out this way. Now, this might look funny at first because you've got a term here that's got a 0 factorial in the denominator, but actually 0 factorial is just 1. So that first term is actually just 1. We're not actually dividing by 0 in that denominator. Okay, so you should notice that this is alternating, right? You can see the minus plus as it goes along. All right. And now if we just work out what those factorials are, like 3 factorial is 6, 4 factorial is 24, and so on, you should be able to work out these factorials and see the values. Okay? Now let's think about what the alternating series estimation theorem wants us to do. We're looking for a term that's less than 0.005 right here, which is equal to 1 over 2,000 in absolute value. And actually that means we found it. There you can see that we've reached a term that's smaller than 1 over 2,000 in absolute value. So that means we're done, because what that means is the partial sum that we take, if we just take this portion of the series, that partial sum, if we take that partial sum, that means we're summing up to n equals 6. That will estimate the series accurate to within the next term of the series, which is this guy right here. And we know that that number is smaller than 1 over 2,000. And so that means the value of n that we're after is n equals 6. And that's it. All right, that's all for math for today.